know you were fine. We had a lot of time then. Okay, welcome back. That was a booming voice. Before we begin, I want to point out the email to which you should send your PDF slides has now appeared magically on the projector over there, so please do so for speakers who have already presented, anyone else who's ready to do that. Are we ready? Okay.
Yeah, sure.
Good. Sorry. Keeping on our theme, where the next speaker is Rychard Bouwens. We'll be talking about the, I think, the stellar mass halo mass relation above Redshift 4 using HST and Spitzer data.
Yeah, well, that will be that work is still in prep, but so I won't actually have time to touch on this much. Again, it's great to be here in Santa Cruz. Love being here. Home for many years, and it's nice coming back. So what I'm going to be talking about is primarily work based on the frontier fields, but I'm going to start out by just talking about by introducing a project that we're working on involving HST+Spitzer data to look at the stellar halo mass relation. So as many of you know, basically the stellar halo mass relation is pretty universal important, and it's pretty much fundamental for understanding galaxy buildup, etc. Basically, it's fundamental relation guiding how many stars are formed per unit halo mass as a function of halo mass. And this relation appears to not evolve substantially across cosmic time overall, but there are some hints of some possible evolution. Here is a fairly recent work providing new observation constraints on this relation, basically between Redshift 4 and 7, from Harakani, the HiPACC survey, probably the most comprehensive look at this so far, because they are able to provide constraints. Do we have a, do I have a pointer? Oh, it's kind of useful. Okay, so yeah, so basically they provide constraints up here, and oh, okay, well, they provide constraints up here, and basically it suggests no evolution. However, there's a great amount of evolution over this range here between Redshift 4 and 7, where in principle, the efficiency of integrated efficiency of star formation increases from Redshift 4 to 7, suggesting star formation is more efficient at very high redshifts. However, this is very difficult to constrain because of uncertain stellar mass measurements. It's very basically at these redshifts, we don't have much leverage to constrain stellar mass. There's not the Spitzer data that we have available is contaminated by lots of nebular emission lines. So we've been trying to essentially look at this by essentially obtaining SED information on the very highest redshift objects. This is challenging because the SEDs are very low signal to noise. So we've been essentially combining all existing HST+Spitzer data for redshift greater than 5 galaxies to essentially provide constraints in the SED shape. Basically, our results are suggesting that essentially that they're consistent with these redshift 7 galaxies having mass to light ratio consistent with 0. It could have another mass to light ratios, but basically consistent with essentially a zero-age population, suggesting that, so there's been a lot of discussion about this plot. Basically, it's consistent with previous results, but also consistent with much lower results. So basically, the SEDs are consistent with the galaxies having formed all their stars almost instantaneously. So that's one thing that's in prep. Okay, so let me now go on to the main topic of my presentation. I'm going to be talking about the prevalence and size of the faintest galaxies in the universe. I'll be talking about the faint end of the UV luminosity function from the frontier fields. Now, the frontier fields are great, allow us to do lots of different things. However, essentially going out there and getting constraints on the faintest galaxies is very, very challenging. And essentially, there's been a lot of steps in the steps necessary to essentially make it there. Lots of things that turn out to be much more challenging, and so there's many different papers that have been involved in going about doing this. Why do people care about the faint end of the luminosity function? We'll see, talked about this earlier and many other presentations. Faint end of the luminosity function is essentially important. Here I show you field constraints based upon the candles plus UDF fields. These things are interesting because essentially they can provide valuable photons to reionize the universe. With current constraints, we can, L star is roughly here, we can probe basically 40 to 100 times fainter. Basically, the question is what's here? It's an important reservoir of ionizing photons. And presumably, and basically at the bright end, we would get roughly 50% of the ionizing photons. The faint end could essentially provide the other 50%. So in principle, it could be an important reservoir of ionizing photons, potentially doubling what we get from just using the brightest galaxies which are observed. Another reason that it's of interest to look at the faint end, again, was discussed in the previous talk, is basically trying to understand the physics of star formation at the in the lowest mass halos. Basically, here are some predictions from the Kroc survey showing, it looked like someone else was putting laser point. Kroc survey showing the predicted potential turnover in the luminosity function, and this turnover could be expected from inefficient cooling, radiative heating, from cosmic reionization, essentially putting in the turnover. So actually exploring this observationally is of great interest. And the technique that the community has been using is gravitational lensing, basically taking advantage of lensing clusters to try to push very faint. And so there's been a major effort to do this using the Frontier Field program, basically combining the power of very deep imaging with Hubble, a la in the Hubble Ultra Deep Field, with gravitational lensing from lensing clusters. There's 6 lensing clusters plus deep parallel fields. And so this is all great. And so in principle, this allows us to potentially go a factor of 10 fainter. And so we actually have large samples available to probe this. This is our newest large samples at Redshift 6 using all the 6 Hubble Frontier Field clusters plus parallel fields, having a sample of order 750 Redshift 6 galaxies. They're effectively state-of-the-art sample sizes. There's been a lot of emphasis previously about these things, and this is effectively 7 times larger than any selection in literature. I guess if I include my own, maybe 5 times, 4 or 5 times larger. Okay, so can use these samples to constrain the form of the luminosity function to very faint magnitudes? And the answer is yes. Here were our own constraints at Redshift 6 using 4 clusters based upon our results in prep. These are the 68-95% confidence intervals. Obtaining results require assumptions about the errors in the lensing models. So it's 1 result. Now we're basically, this is kind of small, so this is again preliminary, so this could be a little bit model dependent. So should you treat luminosity function with the Hubble frontiers with caution? And I think that we're learning collectively as a community that this sort of needs to be done. I'd just like to show you basically some differences, some earlier luminosity function results in the Hubble frontier fields. Here's the Lavi result. Here's some Livermore result, basically at Redshift 2 and Redshift 6. And so you might think, okay, this is all solved. We just take these values. What I'm trying to suggest in this presentation is, well, this is all very exciting, encouraging work. It's a bit, there's lots of things that need to be done. You need to be careful. There's, gain and slope was claimed to be known pretty well based upon these error bars. And basically there's no break at minus 12.5. And there were a variety of different results which obtained somewhat different answers. Parsa basically got a shallower feign end slope. And we also, in our reanalysis of some of the Redshift 6 cluster results from the Hubble frontier field, we got effectively what looked like to be a lower luminosity function than the Livermore results. So, and so if you just look at this, for example, there was pretty significant differences in the implied results, suggesting that, again, I'm not trying to be negative on any previous work. There's a lot of, I think it's going to take a while for the community to sort of try to understand how to use these things the best to make sure that we get results that don't have any systematics. So basically, one thing we've been trying to do is compare the feign and slopes that we derive from blank field clusters with lensing clusters. Here's the feign and slope, the luminosity function. The feign and slope is obviously very important because it allows us to integrate the UV luminosity function to very low luminosities. A steep feign and slope implies a lot more ionizing flux or UV flux at very low luminosities. This implies obviously much less. Here are the results from some of the blank field studies. I used some from Parsa myself. Here are some results basically from Olavi, Livermore, several different ways of using their results, different ways of fitting it. And again, there was a bit of a tension. Again, small formal errors would disagree quite significantly. Clearly, we need to understand lensing better. Again, these are probably, so why is it difficult to derive for results from the frontier fields? And I'll just quickly go through a little cliff notes here. So why is it challenging? It's one thing that's challenging because of the large uncertainties in the magnification factors. It's essentially our magnification models for the frontier clusters. Here's max 0416. Here's a result from one group. And here are essentially results from different groups. Broadly, they look pretty similar, but in detail, obviously there's some differences. So, basically, because of these differences, this can impact the luminosity function. And so what impact does this have on claimed sources in the literature? basically I had a compilation of sources from the literature. There's some very faint sources from Ishigaki and Livermore. There's a faint source at Redshift 10 from Infante, who basically included all these. And the question is whether any of these are robust. And so what I've done is now there's new models for the focal frontier field clusters that include even more information, basically including spectroscopic redshifts. And so basically, if you actually include those, a lot of these sources start to become a bit fainter, basically consistent with maybe -13.5, maybe -14, basically. And if you take the one magnification, one sigma, if you assume take the lower 1 sigma limit on the magnifications, it goes down to this. So now we don't have any sources fainter than -14. Yes, I see. Thanks. So we can now, with more data, we have many more sources potentially, and so we in principle have many more faint sources. The challenge, of course, is that many of these sources are also probably uncertain, and so if you use lensing models, a lot of these will probably also become fainter. Fortunately, the community is going to, for some of these, the community is going to be equal. Anyway, so that's just a challenge. So many sources, but there's obviously you have to be a bit worried about sources scattering behind magnifications. So what's the impact on luminosity function determinations? So why do these uncertainties in the magnification matter? They matter basically because if you forward model this entire situation, you can create a universe where you have a steep faint-in slope, -2, that goes all the way down to -13, -12, or you can start with a universe where you have a turnover at -15. You can start with both these universes and then try to recover the luminosity function. And if you try to recover the luminosity function for both these universes, you can get something where you have a faint-in slope of -2. So, and the reason this happens is because you end up having sources that are lower magnifications scattering to high magnifications. And this happens in such a way that it can effectively wash out a turnover if the uncertainties become large enough. So again, this is one thing to worry about. And basically all the results will asymptote toward a faint-in slope of -2, regardless of the input luminosity function. You can also do this with other different faint-in slopes of maybe -1.5. If you do that, you start with an input and create a universe like this, and then try to recover it. You recover something like this. So basically, you recover something where you recover things pretty well at the bright end. The faint end, it basically changes to -2. So basically, all the luminosity functions appear to be steep, independent of the inputs. So it's very difficult to probe fainter than -14. That's the basic point. Okay, so basically, what is the impact on the magnification factors? You can forward model this, and if you make the worst possible case assumptions about the lensing errors, you can essentially have 68, 95% confidence intervals like this, like we derived in our paper. If you assume that the errors are essentially much less, then you can essentially end up with essentially more reasonable or smaller error bars. So another major uncertainty is the sizes of these objects. The surface brightness of these objects represent another major source of uncertainty, and basically you have to pay this into attention. Should we be able to find -12.5 magnitude sources at all? And so just to illustrate this issue to you, I've actually taken the standard size luminosity relation for redshift 6 galaxies and simulated galaxies at -12.5 magnitude with this thing behind one of these standard frontier field clusters. And then you can see it's kind of hard to detect things. If you actually do this, and this is where the sources would be, if you actually, maybe they're impossible to find, if you actually make them much smaller, 7 times smaller than I showed on the previous simulation, they're much easier to find. So again, this is a pretty big issue. And so so this is potentially a huge issue, because if you can't find the faint sources, this is going to have a huge impact on volume density estimates, because the volume density is essentially the number of sources you find divided by the selection efficiency. And if they're super low surface brightness, they're going to be hard to find. So why would they be hard to find? If you use standard size luminosity relation, radius goes as the 4th root of the luminosity. These are all standard relations. Basically, the surface brightness now goes as the square root of the luminosity, which means that these -12.5 magnitude objects have 30 times lower surface brightness than the brighter L-star objects. And so this can potentially have a huge impact on the luminosity function. So let's say we assume that galaxies are point sources. you would derive a luminosity function like this. If you assume that they follow standard relations, you get a luminosity function which goes like this. So they're completely different. And one implication is very hard to show the luminosity function turns over because you can't be sure you're not missing sources. So essentially you get a situation like this, and it's very difficult to know based upon the observations which of these is the case because it's very difficult to rule out that we're not being incomplete. So how large are the faint sources? Well, we've been trying to also look at that, and we've been looking at the size versus luminosity. Luminosity relation. We've been taking a lot of these faint sources. We've been finding the Hubble frontier field and overplotting them on the size versus mass relation. Here are ellipticals. Here are globular clusters. Here are ultra diffuse things. Superstar clusters are right here. If you throw on the galaxies, a lot of these galaxies, if you actually try to fit to their sizes, you get something like a lot of these faint galaxies appear to have, a number of them have sizes of superstar clusters, and a few of them have sizes of globular clusters. Eros Gonzalez had a few nice papers talking about a few systems which have these properties. We've been looking at the whole sample, and this is kind of how they're distributed. So based upon these results that I just showed you, we have hope to think that maybe the size luminosity relation is such that the point source size assumption or luminosity function applies. However, it's very difficult to rule out that this blue line is also not the case. So that's a pretty big uncertainty at the faint end, factor of 3 to 10 uncertainty. There was something in the literature where basically other assumptions were used, and in principle, that would have even given higher values than what we showed there. Another thing you have to worry about is you have to be very, very careful with how you model the completeness at the faint end. So this is kind of important. This shows you if you forward model a luminosity function with no systematics, and then you try to recover it, and then let's say you include significant contamination of the faint bins. It basically doesn't just affect the faintest bin, it affects all bins. So you get something like this. There's some potential thing where there was some value in the literature where there was some indication this might have been the case. Anyway, there's a lot of things, not to throw mud or anything. This is the whole thing is this is very challenging, and there's lots of small steps in making progress on this issue. Another important thing is basically correcting foreground light. Again, some very great stuff was done. Even by Pascal Ushmar group, Berlin, from this Rome group, Rachel Livermore. This shows our own attempts to do this. We can also do pretty well. From this, you can use, by taking account of these techniques, you can select very large samples of redshift 6 sources. Another problem with contamination is you have to worry about potential contamination from the foreground cluster. Here's an attempt to arrive at UV luminosity function at redshift 4. Here's a very careful attempt to try to avoid contamination at redshift 4. If you're not careful at all, then you can end up, and you essentially assume that you're contaminated by essentially cluster galaxies in your luminosity function. You can get something like this. Again, many systematic concerns that we need to concern ourselves about. And so what constraints can we set on the faint end? Again, this is what we initially, this is initially what we came up with a few months ago in terms of our published paper. This is making very pessimistic assumptions about the lensing errors. This is more optimistic. This is essentially being more optimistic, basically forward modeled uncertainties. The error bars may be a bit small because we have assumed a functional form. If we drop the functional form assumption, we may end up having larger error bars. Through the size uncertainties, we essentially have, this is a lower limit. Actually, the true region, it would actually extend upwards. So basically, this has to be a lower limit because of the size uncertainties. So again, many systematic errors to concern ourselves. What about the faint slope? We've been trying to solve this and trying to get self-consistent results between the blank fields and lensing clusters. In our paper from 2017, which is now in the journal, we actually get self-consistent results between the blank fields and the lensing clusters. And now we're trying to work to see if we can get self-consistent results at our redshifts. Yes, I know. Okay. So the cluster determinations agree with field determinations. What we want to do is measure the same faint and slope of the luminosity function. We want to calibrate these lensing clusters as tools to derive Feynman slope very, very accurately. And this is encouraging, and we've been also doing it at other redshifts and also getting very encouraging results. And so we're just trying to finish this all. So work in prep, we essentially have very large samples, over 4,000 objects, essentially at all these different redshifts. This is the results at redshift 6, at redshift 7, redshift 8, redshift 9, redshift 10. We've been sitting there trying to basically get basically full forward model uncertainties on the luminosity function evolution, all these different redshifts, and all the way to the faint end. Okay, so just in summary, so basically, I didn't include this on the point on there. In terms of this stellar mass over halo mass relation, basically, we've been looking at that using really deep stack data, HST+Spitzer stack data. Those results are consistent with basically the stellar mass, the halo mass relation at redshift 7 and 8, not evolving at all. So basically, based on the SED results, we still don't think there's any robust evidence for evolution at redshift 7 and 8. In terms of the frontier field results, basically, gravitational lensing is obviously a great tool for probing the properties of the faintest galaxies. There's a lot of important sources of systematic error, uncertain sizes and surface brightnesses, imperfect gravitational lensing models. There's a bunch of other minor issues we presented. We have methods to overcome the first two and also the other ones. We've been trying to come up with methods to do that. We basically derive completely self-consistent Feynman slopes from the lensing clusters and the field. Basically, we get this minus 1.92 value, which is essentially completely consistent with the value from the field and from all the other studies in the literature. It's very difficult to rule out a turnover brightward of minus 14. Although the new results suggest that we might. Results at other redshifts are in preparation. All those results seem to be, we're able to get pretty good agreement between the field and the cluster results. And by fitting to the sizes and the profiles of the objects, we find that many of these objects may have sizes as small as 20 to 100 parsecs. So there may be many, many very faint, small star cluster-like galaxies hidden in the Hubble frontier field. Okay, that's all I have to say.
We have time for maybe one question. We'll start with Avishai.
Well, what it means is, what I mean by zero is that basically, if you look at the SED, you basically get something that looks like, you basically don't see a bomb or break. You see something, you basically see just a blue UV continuum slope that continues all the way down until you get to these nebulous, very strong O3 line, and then you see a strong O3 line, but you essentially see something that just looks like, the SED looks completely consistent as with something you would get it was like 10 million years old. And that's based on the stacks of these very large redshift 7 and 8 samples. It doesn't mean zero, it means it's consistent with zero. We don't know what the mass to light ratio is. If you have, let's say you have you just say an instantaneous burst and it's 1 billion years old. It could be very, very low. It's consistently being very low, but it could be higher because you can still form stars for a while without actually seeing the impact.
One very short question. Let's go ahead and switch. Let's go ahead and switch the.
Yeah, that's right. Yeah, that's right. That's right. I mean, it was just, it's basically something I was just trying to work out just to see if it could work. So at redshift 6, 7, 8, 9, 10, it's almost certainly not an issue. However, you can also try the same experiment at redshift 4 and 5. And if you look at things at redshift 4 and 5, you can actually, if you actually go through the process of computing the luminosity function to like including sources of 0.9th magnitude, you see that the luminosity function is systematically higher than it is if you take great pains to avoid contamination. If you just kind of include everything without thinking about it, if you use a very conservative sample selection, you get a luminosity function at, say, at redshift 4 or 5, which is substantially lower than if you just go hog wild and include everything. And it's different by like a factor of 3 or 4. So it's actually quite substantial. So it does suggest that say, at redshift 4, and I also can see it at redshift 5, it's a little bit dangerous, particularly if you go to 29th magnitude.
Okay, let's thank Richard again.
Yeah, sorry.